Welcome to the module 2.1 lecture number 2.1 and part B. In this particular lecture, we will cover the second type of errors that we can found in every computational devices known as machine precision or round of error. Machine precision is nothing but the least count of any machine which we are using for the numerical computation or the numerical techniques. We can also define it as a least count of a device actually. For that, we have to understand the machine, what is machine precision. For a laptop and for any computation device, we expect it has the infinite precision, but that's not true. Every machine has its own machine precision or the on its limits. For more understanding the machine precision, we have to assume that we have a rule of 30 centimeter, and as we all have known that the or the precision of a ruler has 0.1 centimeter or 1 millimeter is the minimum resolution of the ruler. So we cannot measure the length uh, less than 1 millimeter or 0.1 centimeter by the ruler. For precision of or the for the measurement of less than length of 0.1 millimeter or 1 millimeter, we use another scale called vernier caliper. It also has a least count. As we all know, that every device which we are using for our numerical techniques has a least count. It has so we are at the vernier caliper. The vernier caliper has a better precision than the ruler. Just like these devices, a real number also has a least count. This is the important line, that a real number also has a least count, because we are going to use it in a MATLAB. Machine precision is depends on the number of bytes to store a real number. Let me explain how it depends on the number of bytes. Suppose that we have um, a computational machine, and it stores a 4 bytes uh, on a standard number. Okay, computer has stored a standard number in 4 bytes, which is basically um, 64 bits, and you can know that it has a least precision. And when we use a double number, it is stored in 8 bytes, in 16 bytes. Sorry, that is my mistake. It is a 16 bytes, and it has the more machine precision. As we going further, and we can go we can just see that every standard value has a less machine precision, and a double number has a more uh, accurate values with least precision. So, for more examples on or the most computational technique courses, you can go to this NPTEL's website and course for. Um, in the previous slide, I just um, took you the introduction of machine precision, which depends on the number of bytes. So in next slide, it will take us a new it will take us at a new definition, which is a floating point representation of a point. So let us take a device which has the machine precision of 10 to the power minus 5. So we have a 0 point, it will start with the zeros. So 0 point x times 10 to the power x. It basically gives us a mantissa of a number. So it has the machine precision of 10 to the power minus 5. Let us take the example of numbers in that particular machine of mantissa is 10 to the power minus 5. When we took the example of 23.217, it will write in, in that particular machine, it will write it as 0.23217 times 10 to the power minus 2. So all the number gets stored in that particular storage of that 10 to the power minus 5 machine precision. Let us increase the value of a number called 23.218. It will become 0.23218 times 10 to the power minus 2. So it is also got stored in that particular device which has the machine precision of 10 to the power minus 5. As you all can see, when we increment a number, it also get increased. But what happened if we increment the number by the doubles? Okay, so let us take an example, 23.21872. It will becomes 0.23218. Why this? Sorry, it's my mistake. It won't 7. Okay, so why this 2 got disappeared from storage? Because the machine precision has only storage of 10 to the minus 5, which means it can only store 5 elements of that particular number after 0. So at here you can see we have six different elements of that particular number, so it can only store the first 5 elements of that particular number. So it's stored in that, and 10 to the power minus 5 as the exponent. So as you can see, for that particular machine, the 23.2172 and 23.217 becomes equal. Okay, for that, thus we can say that the least count of that particular decimal machine has 0.10 to the power minus 5 and absolute x. Okay, so it has the machine precision of minus 5 order. So for MATLAB programming, MATLAB has an special keyword to find out the precision of MATLAB. So let's start the MATLAB. And what was that particular keyword to find out the machine precision of a MATLAB? So that is EPS. It is the keyword to find out the machine precision of a MATLAB. So as you can see, when you would enter, it will give you a value 2.2024 and an exponent of 10 to the power minus 16. So it has the machine precision of 10 to the power minus 15. It means it cannot get result when the machine, when we counter, or when we want to find out result of when we found out the result of any particular number with its least value. So 10 raised to power minus 16 is the least value of MATLAB. Okay, it is equal to the 2 caret 2 into 2 caret minus 52. It's not actually, it's cannot execute the number. We just got multiplied it with 2, so it will not it is just like 2 caret minus 52. So as you can see, we just let ignore this particular command and focus on that particular. So as you can see, the machine or the least count of MATLAB in the order of 10 to the power minus 16, and the and the and the number which has 2 raised to minus 52 got the same value. Why this happened? Because the MATLAB uses the um, double precision of 10 raised to power minus 52. So it has the double values with the least value of 10 to the power minus 52. Okay, so let's do some operation on that particular least count. A is equals to, let's define it. A is equals to um, 1 plus 2 caret minus 52. It will basically give us a 1, because this value has 10 to the power minus 16, and which will, when we add a particular one number, it will count as after 1 the 1.0000000 until the minus 16. That particular value has encountered after 0.00 until 10 to the power minus 16. And let us example an attitude a minus 1. It will give me the this particular command will give me the um, this value or the least count of MATLAB. Why? Because as you all know that a has the value of 1, but it has also contained this particular value, which was 10 to the power minus 16 of least count of MATLAB. So when we subtract 1, it will just basically subtract this one and the other remaining part of which is also known as the machine precision of MATLAB. We got this as a result. So as you can see, we got this as a result of that particular command. So let's go beyond the machine precision or beyond the least count of MATLAB. Let us define a with the new least count called 1 plus 2 caret minus 53. What would happen at here? We go beyond to the least count of MATLAB and say what would happen at here. So as you all know, when we just enter, it will give us simply 1. It just not count the least count of MATLAB precision. The MATLAB uses that particular double precision. It does not count it in it, and it just simply give us 1 without any adding particular machine precision of MATLAB. So that use the same command or the same. What happened at here now? At that particular command, it will just give us 0 or the null value, because a has its new value, which is 1, simply 1 without any uh, least count of MATLAB. So it will give us 0. As you can see, we got a 0 over there because it is not added, or it will not count if the beyond, when we go beyond to the machine precision or the least count of MATLAB. So we got an error at here. It is just like an error because we cannot count beyond the limit of MATLAB's double precision. Noted down, the EPS has the main keyword to find out the machine precision or the least count of MATLAB. By this, I'm going to end off this particular lecture. Thank you very much for joining us.